Okay, so we've been doing derivatives this whole time, and we've only been doing what's called the first derivative, meaning we've only taken the first derivative. We've only performed the action once. Section 3.5 is about higher derivatives. So higher derivatives. So kind of the motivation for this is think about a curve f of x that looks like this versus a curve f of x that looks like this. So both of these curves have positive slope. You can see that they all have positive slope. Anywhere I put a point, the tangent line has positive slope. So they're both increasing. So these two curves are increasing, but they're increasing in a different way. And so we want to have some form of derivative that tells us that these are increasing in a different way. So here, if I draw a tangent line, and then draw a tangent line here, what's happening to the slopes of the tangent line as I move from left to right? Here it's relatively flat, and then it's getting steeper and steeper and steeper. So the slope of this tangent lines is increasing. So the slopes of the tangent lines are increasing. Over here, if I draw a tangent line and then draw another tangent line, you can see that the tangent lines are becoming more and more flat. So here the slopes of the tangent lines are decreasing. Tangent lines are decreasing. Now, how do we represent that? Well, think about how do we represent f of x increasing? So f of x increasing meant that f prime of x was positive. Right, so if we want to talk about a function increasing, meaning the slopes of the tangent lines are positive, that meant that f prime was positive. Now, if we want to talk about the slopes of f of x increasing, then we look to the next derivative, which is called the second derivative. So f double prime of x is positive. So over here, we had that f prime of x was positive, but f double prime is going to be negative because the slopes are decreasing. So this is kind of the motivation behind looking at higher derivatives, is that we want to be able to differentiate the way in which a curve is increasing. Is it increasing in a way that the slopes of the tangent line is also increasing, or is the function increasing in a way that the slopes of the tangent lines are decreasing? So that's what the motivation is behind the higher derivatives. So I've already said this a couple times. The second derivative, which we're going to do a lot of work with, the second derivative can be denoted f double prime, y double prime, d squared f over dx squared. This would be your alternate notation. What does this mean? The d squared says take two derivatives of the function f. The dx squared means take the derivative with respect to x both times. So this is your other notation. What we're doing though is just taking a derivative again. So it's the same process as before, only now we're taking the derivative of a second function. Let's do an example here. Let's let f of x be 1 over x squared. And let's find the first 5 derivatives. First 5 derivatives. Then I want to find f triple prime of 2. So triple prime meaning I'm going to have 3 little tick marks here. I'll find the third derivative and plug in 2. So let's start this on another piece of paper. I have f of x was 1 over x squared. I'm going to write that as x to the negative 2. So I usually want to get in the habit of writing x to a power, so there's x to the minus 2. Now let's find the first derivative. So for the first derivative, use your power rule. I'll bring the negative 2 out front, subtract 1, and get x to the minus 3. Now to find the second derivative, I just take the derivative of the previous function. So the derivative of f prime, bring your negative 3 down so we get positive 6, x to the minus 4. Now let's find the triple derivative. So again, using the power rule, I'll get negative 24x to the minus 5. Usually anything higher than 3, we start putting it in parentheses. So the fourth derivative would be f to the 4 in parentheses of x, because it gets confusing to have so many check marks. Multiply again, so let's see, 24 times 5 is 120, x to the minus 6. And then lastly, my fifth derivative, negative 6 times 120 is negative 720, x to the minus 7. So those are my first 5 derivatives. Now this isn't anything new, only I'm just taking derivatives over and over again. So to answer the other question, what was f triple prime of 2? That means plug in 2 to my triple derivative, or my third derivative here, so this will be negative 24, 2 to the negative 5th, and plug that in your calculator, negative 0.75. So I found the first 5 derivatives, then the question asked what was f triple prime of 2, plugged in 2, and that's what I got. Let's do one more example. Let's find f double prime of x if f of x is e to the x times 2x squared minus 3x. Okay, well to find f double prime, I'm first going to have to find just f prime. So f of x is e to the x times 2x squared minus 3x. So to find f prime, I'm going to have the product rule. So u was e to the x, v was 2x squared minus 3x. Now let's find u prime and v prime. So here u prime is going to be e to the x, v prime is 4x minus 3. So that tells me that my first derivative is u prime v, so e to the x times 2x squared minus 3x, plus u v prime. There's my first derivative. Now I got to find the second derivative. So the second derivative, I am going to have to find the derivative of e to the x times 2x squared minus 3x, and the derivative of e to the x times 4x minus 3. So this is actually 2 different product rules. So I have my first product here, my second product here. So let's go ahead and let my u be e to the x, my u prime be e to the x over here. My v was 2x squared minus 3x, and my v prime was 4x minus 3. Now for the second product, I'll let my u be e to the x, and again my u prime be e to the x. Then I'll let my v be 4x minus 3, and my v prime be 4. Which tells me that f double prime of x, well my first product, let's see what I get. For my first product, the derivative was u prime v plus u v prime. And now from the second product, I'm going to get that the derivative is u prime v plus u v prime. So to find the second derivative, I had to use the product rule twice because each one of these was a product. So I just found the derivative of the first, added it to the derivative of the second, keeping in mind that to find the derivative of each one, I had to use the product rule. So there's my second derivative. Now let's talk a little bit about, in terms of position, velocity, etc., what is the second derivative measuring there? So let's think about the units. So let's let s of t be position. Let's say position in meters. What is v of t measured in? If we go back to what v of t was, that was ds dt, which is being measured in meters per second or meters per minute, whatever t was measured in. What's the derivative of v prime? So the derivative of v prime is going to be dv dt, which will be meters per second, which is meters per second squared. So do we know any units that are in meters per second squared? Or do we know anything that we've seen before that we measured in meters per second squared? If you go back to the gravitational force, it was measured in meters per second squared, and this is called your acceleration. So v prime is acceleration, which we'll say a of t. So what to take away from that? S of t is position. V of t, which is equal to s prime of t, is velocity. And then a of t, which was v prime of t, which is the second derivative of the position, is your acceleration. There is a third derivative called jerk. We're not really going to do much with that, but if you do know what the next formula is, it's the jerk, and that's the third derivative of position. So if we have an equation for position, we can find an equation for velocity, and we can find an equation for acceleration. So let's do an example where we use these three things. So let's say that a ball is thrown in the air with height's going to be measured in meters, given by S of t is 5 plus 2t minus 4.9 t squared. T here, t is going to be measured in seconds. A couple questions that we want to find. What's the acceleration after 2 seconds? What's the velocity after 2 seconds? When does it reach its highest point? So when does it reach the max height? And I also want to know what is the maximum height. So four questions here. I'll write the next one on the next page, but we have a ball being thrown in the air. The height's given by this equation. And we're going to know what's the acceleration after 2 seconds, what's the velocity after 2 seconds, when does it reach its maximum height, and what is the maximum height. Okay, so to answer these questions, especially since the first question is dealing with acceleration, we're going to need to find equations for velocity and acceleration. So let's do that first. So S of t, 5 plus 2t minus 4.9 t squared. V of t is the derivative of S of t. So I just take the derivative of my position and I'll get 2 minus 9.8 t. And then acceleration is the derivative of v of t, so I get negative 9.8. So those are my three equations that I can find just by knowing the equation for position. I can tell you what the equation for velocity and the equation for acceleration are. Now let's go through and answer our questions. First one, what's the acceleration after 2 seconds? So that's saying what is a of t? Well, a of t is just a constant function. So negative 9, and the problem was measured in meters per second squared. So the acceleration after 2 seconds is just a of t. This is a constant function, so it's always negative 9.8 meters per second squared. Second one, what's the velocity after 2 seconds? So that's asking the question, what is v of t? So I get 2 minus 9.8 times 2. What do I get when I plug this in? Negative 17.6 meters per second. Now we got a negative velocity. What does that mean? That means that the ball is falling down. So it was thrown up in the air, had positive velocity, then it started falling back down, and that's where the velocity became negative. When does it reach its maximum height? So go back to what we were doing before. What happens at the maximum height? So it's kind of like the ball is thrown in the air if we're measuring height here. And we're measuring time along the x-axis. The ball is thrown in the air, then it reaches its highest point, and then it starts coming back down. At that highest point, I had a horizontal tangent line. So to find this time, what I want to find is where is velocity equal to 0. So the max height happens when the velocity is equal to 0. So we're going to solve this equation. So the velocity was 2 minus 9.8t. Let's set that equal to 0. 2 equals 9.8t. Divide both sides by 9.8. T is going to be 0.204 seconds. So after 0.204 seconds, the ball reaches its maximum height. Last question, what is the maximum height? Well, I know when it occurs. The question is, what's the height there? Well, that's given by position. So this is going to be S of 0.204. So I plug in 0.204, that's 5 plus 2 times 0.204 minus 4.9 times 0.204 squared. And I get 5.204, and that was measured in meters. So to find the highest height, I found where did the height occur? Where did that maximum height occur? And that was where velocity was equal to 0. Then to find the highest height, I plugged it into my position and got 5.204. So by looking at higher derivatives, we can find acceleration. We can find the jerk if we need to. We can talk about concavity, which is what we were looking at in the graph. So we can talk about the rate of the slopes increasing, the slopes decreasing, things like that. So the higher derivative actually tells us a lot about the function, and especially acceleration.